Okay, so now we're getting into a new chapter in the notes. We're actually going to look at solving systems of linear equations. And we'll get past the stuff you would have seen back in the first linear algebra course, but I figure review can't hurt. Actually, chances are next week my PhD student Amber Sumner will be taking over this part. So, all right, so let's get this Valentine's Day lecture over with.
Short for Valentine's Day, right?
What?
It's going to be short for Valentine's Day, right?
Well, actually, it depends kind of on you guys.
The month of February.
But that already means fewer lectures, so nice try. But plus the fact that we have Mardi Gras break.
So then you're going to skip Thursday on
Actually, we are, yes. Because Thursday is when we're coming back from Atlanta.
so you'll be too tired.
Yes, I will be. And so we'll have a class that's coming with me. Okay. But I want to allow a little time, or should have a little time anyway, from basically what I cover now, for any questions on the homework. Will you have questions on the homework? Not really?
Some of it.
Okay, well,
not definite questions, because
yeah.
I don't have the time to go in depth.
Okay. Good to know. All right. So, the problem we're going to look at is A equals B, where A is n by n, also invertible, also known as non-singular. X are unknown, so n vector, column vector, and so is B. So the two pretty generic questions that are good to ask when designing an algorithm to solve any problem of this kind is in what cases, what steps of these problems, we're assuming that A can be any n by n invertible matrix. Is this problem easy to solve? And then, after answering that, how can we reduce a general problem to an easy one? Okay. Although this reminds me of one of my many nauseating math jokes, or mathematician jokes. So a guy goes to see a career counselor to find out what kind of job he should do. And so one test that the counselor gives is there's a stove, and there's a table, pot of water on the table, and he says, boil the water. So he picks up a pot, moves it over to the stove, flips on the burner. Next test, the same situation, except now the pot is already on the stove. So he says, boil the water. Well, he moves the pot to the table, then picks it up, moves it back to the stove, and flips the burner on. And the counselor says, well, you should be a mathematician. Like, well, why? Because you reduce a problem to a previously solved problem. And yes, I got plenty more. Okay, so for this case, we're trying to reduce a generally harder problem to the easy case. So an easy case is if A is triangular. So A is a matrix of this form, and it doesn't matter whether it's lower or upper triangular. We'll use upper let's suppose that B is something like that. So in this case, it's easier to see if we write out the system of equations that this matrix in right-hand side represents. So we have x1 minus 2x2 plus 3x3 equals 1. And then 4x2 minus 5x3 is minus 1. And then 6x3 is equal to 2. So in this case, since one of the equations, the third one, is decoupled from the others, that it can be solved independently, so you can just go ahead and set x3 to be, so just a simple division gives you your last unknown. And then once you have that, then you can say that x2, so if you rearrange this equation for x2, so you get minus 1 minus 5x3 all over 4, but then your value of x3 can be substituted, bless you, in there, and then finally x1, so if you rearrange this equation for x1, you get 1 minus 2x2 minus 3x3. So that same value can be substituted here all over, well, 1. And then the value of x2 that you get can be substituted in there. And I'm not going to bother doing arithmetic on this. And this is called back substitution. For the case where A is an upper triangular matrix. And then similarly, forward substitution for the case where A is lower triangular. And we'll make use of both of these. So in the case of forward substitution, the first equation is separated from the rest. You solve that, and then you compute the unknowns in order from first to last instead of last to first. Okay. So now, okay, so I can fill that in here. Now, of course, this is not the easiest system to solve. By far, the easiest system to solve, well, okay, the easiest one of all is that A is identity. But, or if A is a diagonal matrix, then you n divisions and you're done. But that would really be overkill, because if you go with a simpler problem for your category of easy problems, then there's more work to do to reduce it to that case. We actually want if you figure this way, the hardest problem that's easy to solve, because then the reduction task is easier. And for that, we're going to learn about it first in the algebra class, using row operations. Review the three kinds of elementary row operations. The first one is scaling a row. Of course, whatever you do to one side has to do to the other. So this is affecting both A and B. The second one is interchanging two rows. But certainly, these are kind of operations that would leave the solution of a system unchanged. That's essential, of course. And then, well, most useful one to us is adding a multiple of row I to row j. So in other words, you're replacing one of your equations with a linear combination of equations, including that equation itself. So that will leave the solution of the system unchanged. Okay, so I have more pages here than I would expect to need today. All right. So as an example of how we can use at least a third operation in particular. So we have okay, you can write this out in matrix form, but our system at the beginning so here's our system. It corresponds to AX equals B, where A is our matrix of coefficients. So we have 1, 2, 1, 3, 2, 4, 4, 4, 3. And then our right-hand side B is 5, 17, 26. Okay, so what I'm going to do is use row operations to reduce this system to an upper triangular system, and then we will formalize that into an algorithm that can be coded up, like in MATLAB, for instance. And for this example, I got all the numbers to work out nicely every step of the way, which is harder than it looks. Hopefully Abby will be here soon.
Yeah, she texted me, said she was. She said she was.
Oh, okay.
Yeah.
All right. Okay. So what we can do is, all right. So I'm going to, we'll see this term in your alpha course, augmented matrix. AB, and that's just a convenient notational device so that we can ensure we're doing the same operations on both sides, the equals. So what I'm going to do is, I'm going to work on the first column. So I want, first I want to target these entries. I want to make them equal to 0. To make this system upper triangular. So I need to find a multiple of this row and what I'm going to do is subtract from row 2 and then row 3 to make those entries 0. So I can say that first I'm going to say row 2 is equal to itself minus, and in order to figure out what to cancel, well, like in this case, the numbers work out nicely, like I said. So it's easy to see that you're going to subtract 3 times row 1. So for this row, 3, 2, 4, I'm going to subtract 3, 4, 3. That will cause this entry to become 0. Okay, so 1 is 2. Okay, so that's that. And don't forget the right-hand side, so you get 2 there. And then I haven't done anything down here just yet. Okay, so we've zeroed one entry that's below the diagonal. And now we do it again to target this entry. So, again, because numbers work out nicely, it's easy to see what to do. So third row is itself minus 4 times row 1. Okay, so I get 0 here, and then, what am I saying, minus 4, minus 1. Okay. Okay. Now, we're actually almost in, oh, I knew something was wrong. It's supposed to be a minus 4. Okay. Yeah, because believe it or not, 2 minus 6 is minus 4. Okay, everything else is fine. Now, the last entry I need to eliminate is this one. So now I can just subtract the 2 rows. All right, so row 3 is equal to itself, and I'm going to use row 2 now. I don't need row 1 anymore. That would actually mess things up. So R2. Okay. So now that entry becomes 0, and then minus 1, we get minus 2, and we get 4. Okay, so now the system is upper triangular, and you can use back substitution. So your equivalent system if I were to write it out in full, would be, so, well, first equation doesn't change at all. Okay, so then minus 4x2 plus x3 is equal to 2, and then minus 2x3 is equal to 4. So we see right off the bat that x3 is equal to minus 2, and then you can use that in your equations, solve for x2, and then x1, and that's it. So this is how you proceeded, no doubt, in your first linear algebra course. Now, okay. So now what I'm going to do is describe this process formally. So what we have here, this is called Gaussian Elimination, which is interesting because Gauss had nothing to do with its invention. Gauss lived just a few hundred years ago, and it's been known like thousands of years that the Chinese were doing these kind of operations. Okay, now, so for a little trivia, who can tell me what this form of matrix is called? Once you get it into this form, it's upper triangular, and that's the term that I'll use, but in your typical linear algebra class, what do they call that? Row echelon form, yeah. And you'll never hear me use that term again, because this is a numerical linear algebra class, not a linear algebra class. And it may not seem any different right now, but it will. Okay. Now, in this case, the numbers worked out nicely, but if we consider in general, let's suppose you are trying to reduce your matrix to upper triangular form, and you have some diagonal entry, because notice what we're always doing is, for a first column, we're using the first row to do the elimination. When we need to zero an entry in the second column, we're using a second row. And it's the interplay between the diagonal elements and elements in the same column below it that we're going to determine which multiple of a certain row to subtract from another. So more generally, we have some diagonal entry AII that we're going to use to eliminate an entry, actually you can call this AJJ, and then we have an entry AIJ down below. So I has to be strictly greater than J. So we want to find a multiple of this row to subtract from this one. So our new AIJ, which is supposed to be 0, is given by taking the row itself and subtracting some multiple, which I'll call Mij, times the diagonal entry, because it's this row, row J, that were some multiple of it is being subtracted from row I. So if we see only what's happening in this column, because everything is determined by that, and then that's just used to update all the entries over here. So a new ij, which is supposed to be 0, is itself minus this quantity, Mij, and this is called the multiplier, times a jj. So that multiplier is the scaling factor that we use for the row operation. So since this is supposed to be 0, we can just solve for Mij. What is Mij?
Wait, that's AIJ, AJJ?
Yeah, Aij over Ajj. Okay. Which means Ajj better not be 0. We can't have any 0 diagonal elements. Now the way we can get around that is to do row interchanges to make sure that your diagonal entry is non-zero. And when we get to pivoting later, which is actually something that probably Amber will cover next week, she'll get detailed there, because that part is going to be significantly different than what's done in a 326 setting. Okay, so now that we know which row operations to perform, how to get the multiple of each row to subtract from any other row, that's really the key step in formalizing this procedure. So first, we take into account the fact that we're moving through each column one at a time. So I have a loop. I can use J is normally used in this kind of class for a column index, so I'll do that here. So J is counting from first column, second column, and then this is a square matrix. So we don't need to do anything in the last column. We can stop at column n minus 1. Okay. So our outermost loop, its job is to eliminate all the entries in a column J, below the diagonal. Okay. Now, within that column, like I said, if I'm going to eliminate entries below the diagonal, so now I'm going to have another loop, and I'll use I as usual for a row index. So you're going to start below the diagonal, so your diagonal entry is in position JJ, so I go right below that, and I'll keep going all the way to the bottom. Okay, so we're looping over each row below the diagonal. Okay. So in here, the job of this part what I'm going to fill in here is to perform a row operation. So row I is equal to row itself minus a multiplier times row j. So all of that goes in here. Well, first we need the multiplier, but now we have a formula for that, so I'll fill that in. So this is aij over ajj. So we're assuming that no non-zero diagonal entry is going to come up. Welcome. Is it raining out there?
Yes.
Oh boy, 'cause I was supposed to drive to New Orleans after this class.
Oh.
It's gonna be fun.
Be careful, it's supposed to be bad.
Yeah, so I heard. Well, at least I can afford to take my time. Okay, so now that we have our multiplier, now we can actually carry this out. But the thing is, we're going through all the or several entries within a row, so that requires another loop. So if I were to say I need a different loop variable, so I'll use k, and k is going to be a column index. So, so I can say my new aik, and now the thing is, if I look at where I'm at in row I, everything to the left, so columns 1 up to j minus 1, that part of the matrix is 0 already, so I don't need to touch those columns. I'm only interested in columns j, j plus 1, j plus 2, and so forth all the way to the end. So that's the only portion of this row, but it's still non-zero. So now I can say my new entry, aik, is going to be itself minus the multiplier times the corresponding entry in row j. So what indices do I need to put there? JK. JK. That worked out beautifully. Because they had planned that. And what's interesting here, note, this is kind of like in the matrix multiplication formula, where the second index of this entry matches the first index of the other. Okay, so that performs a row operation. And then, I have to keep in mind though, my augmented matrix, my last column is B. I have to update B also. So that's going to be similar to this. So BI, that only has one column, it's a column vector, is itself minus a multiplier times BJ. Okay, so that completes the algorithm, except there's one thing here that's actually a bit wasteful. In this loop, so I've intentionally made a mistake, or just put in something useless. There's no need to look at column J. I mean, the row I is not zero from column J all the way to the end. But for aij, the whole point of this is to make that entry 0. We know this is going to be 0. So we don't have to actually carry out the computation. So
Start k, j plus 1.
bingo, yeah, and that's actually what it says in the notes. But I wanted to emphasize that we really are trying to minimize how many arithmetic operations we perform. So don't perform something that you know what it's supposed to do. Okay. All right. So that is so it is a nice case where if we never have to deal with any non-zero diagonal entry, which is not always going to be the case, then this will do it. This will reduce A to upper triangular form, and then the right-hand side B will be acted on appropriately to get the right-hand side for the equivalent system. And then you can go ahead and do back substitution. Okay. Now, I should mention the cost of this algorithm in terms of arithmetic operations. That can be quite a pain to come up with a precise expression, but roughly 2/3 n cubed floating point operations. Now, floating point operations come from this division here, and this subtraction, this multiplication, and also multiplication and subtraction over here. And you kind of see why the cost would be proportional to n cubed, because we have 3 nesting levels of loops, and those loops can take as many as roughly n iterations. So there's no surprise that we got 2/3 n cubed. So that can be pretty bad. We try to avoid having algorithms that take that much time. On the other hand, once you do all this and it's time to do back substitution, that's going to be cheaper. So run the algorithm for back substitution. Any questions about the Gas elimination algorithm? So this would be something that would be pretty easy to code up in MATLAB based on this pseudocode description. Just have to adjust the syntax. Now, okay, so in the case where A is upper triangular. So as I showed you in the example, we start from the last row and work our way out to the first. Okay. Now, what you also saw in the example was I start with the right-hand side value, and I have to subtract this is to solve. Oh. Okay, I need to change my notation. Instead of x equals b, solve ux equals y. U is upper triangular. Okay. So the first thing you do is you set your unknown, so trying to compute xi, is what do you have on the right-hand side? Yi. Now, okay, I'm going to redraw. Shouldn't have erased it from before, just so you can see where the algorithm comes from. The upper triangular system I had. So as x1 plus 2x2 plus x3 is 5, minus 4x2 plus x3 is 2, and then minus 2x3 is 4. And so in order, x3 was just 4 over minus 2. So right-hand side entry divided by diagonal entry. x2 is 2 minus 4x2 minus x3 all over, no, that's not right. 2 minus x3 all over minus 4. And finally x1 is 5 minus 2x2 minus x3 all over 1. So we're always dividing by diagonal entry, and you're subtracting off terms, but you're subtracting off more and more terms. And I just realized when I moved earlier, Stephanie, let's check your notes. You know what I read now?
What did I write down?
When I was working at steps on.
Oh, yeah, sorry.
Okay. All right. Someone else helps. Oh, well, try best. And you didn't either.
I follow along with the PDF.
Well, okay. I kind of figured you were. Yeah. All right. Well, I'll have to watch the video. Okay. Oh, that reminds me. I don't know if any of you, because you guys are always here. Last class, I wanted to try to prove something about best approximation and projection. And sure enough, after class, I figured something out. So I added it to the video.
Okay.
I wasn't able to do both directions. Well, actually, I looked up later how to do the other direction. I did one direction successfully. The other direction actually requires using an orthonormal basis. I'm like, I'm not doing that. It's not elegant
So
enough.
you were trying to avoid.
Yes. So for one direction, you can avoid it. Okay. Now, yeah. So this is gonna drive me nuts. So I won't know until I look at the video later. Then I think on. I have a feeling that for X2, I might have messed up, but since you guys don't have it in your notes, then that's not a problem except for whoever's watching. Well, that would be like Candace, Samaya, and Vivian. Okay. So Candace, Samaya, and Vivian, this is correct. If it disagrees with what I wrote before and I have no idea right now, this is what you go with. Okay. So this pattern I want to replicate over here for a general case. So the first thing you have in your expression is always a right-hand side entry. 4, then 2, then 5. And now what you need is a loop that's going to subtract off elements of your matrix times previously computed values of your solution. So I can have a loop that starts at, so J is going to be a column index. And you know you go all the way to the last column, and you start with column immediately to the right of where you are. So I plus 1, I don't need this. Okay. So I plus 1, then I plus 2, and so forth, all the way to the end. And that's where you subtract all the terms. So xi is itself minus the entry of a matrix at that point, so row I, column j, times the corresponding unknown that you would have already computed, xj. Now, j is always strictly greater than I, so xi is what you're computing now, xj is something you already have available, so there's no problem there. And then, once that is finished, then you have xi, to finish off, is itself divided by the corresponding diagonal entry, which had better not be 0, uii, and that's the end. Okay, so that's back substitution, and now we have something we can code up to solve a general system of equations, but it will not work every time because we're not prepared for the possibility of having to possibly have a 0 diagonal entry or one that's very close to 0. So next week when Amber covers pivoting, that will be addressed. But this will work for the majority of systems of equations. Now, since I mentioned cost for Gaussian elimination, I need to mention cost for this, much less. So the cost is roughly n squared, which makes sense. We only have 2 levels of loops in this case instead of 3 for Gaussian elimination. So Gaussian elimination is the expensive part. Back substitution is far less. When it's order of magnitude less, that makes a huge difference when you're talking about a very large matrix. So in fact, suppose you're in a situation where you're solving the same system of equations, several systems of equations where the matrix in all of these systems is the same, but the right-hand side, B, is different. So what you should do is go ahead and reduce A to upper triangular form once, and then with each separate right-hand side, you reduce it which costs much less, and then you can do back substitution many times. So you can save yourself some effort that way. That's really a reason to not think in terms of an augmented matrix, because an augmented matrix takes your A and your B and puts them together into one entity, whereas in terms of efficiency, you don't really want to do that. You'd rather just work on A once and then possibly work on many different B's later. Okay. Now, this example that I have in the notes. Oh, this is one that was a real pain to come up with, to make a 4x4 example work with all the numbers nice. But, okay.
If you put that much effort into it, you should do it.
Yeah, well, I think I'm doing pretty well on time. Oh, I have half an hour. Okay. Good to know. Well, first, does anyone have any questions on the homework? Going once?
Yeah, I have started. So I'm having
What did I make it do? The 16th? Or?
like Thursday.
Yeah.
Oh, okay. Well, that explains why. Not that I really care about due dates in a class like this, but okay. Alrighty. That's good. Then I can just focus on that. And then yes, after you all are gone, I'm gonna check the video, make sure I didn't mess this up, because that's gonna drive me batty. I guess what I can do is if I really cared to, I can cut it out in the video. Oh, that reminds me, for those of you watching, I might not be able to get the video up as quickly as normally do, because usually, like on Tuesday, I would do it Wednesday morning, but I'm going to be in New Orleans for much of the day tomorrow for a conference, so it may take a bit longer. Okay.
That message though, it's not gonna help, like, it's not gonna make
I don't know
them,
when they watch.
so they're gonna be mad at you, like mad, and then they'll watch it and they'll be like, oh, I wish I would've known that before, I was waiting, you know?
Okay, so my brain's not working today.
He's like, I'm sorry, this is.
Okay.
You have to upload it before you can apologize.
Well, great, now I got two things to cut out of this video.
Sorry.
Okay.
It was
All
a
right.
good, hey, it was a good thought.
Yeah.
Thought it counts, right?
Yeah.
Maybe you could do like a.
Okay, so
email shout out.
anyway, yeah. So I'm sorry for how long this video most likely took to upload.
There you go.
Okay, yes, past tense is a wonderful thing. Okay, kill me now. Okay. Right. Oh, this is going to be fun. Okay, so now my system is a 4x4. Okay. Okay, so that's my A, and here's my B. Okay. So now I make my augmented matrix, which I'll call A tilde. So A and B slapped together. Four, 9, 3, 4, 22.
I think that's a 4. The 9 you wrote, is it supposed to be a 4?
Oh, row 3, column 2, in A.
Row 3, okay.
Wait.
Oh,
Wait,
yeah.
in A or A tilde?
It's funny because often on the board, my 4s and 9s are hard to tell apart. Okay.
Wait, element B? Is that 5?
Yes.
Not 6 and 22.
Okay. Well, at least since it'll take a while before I can upload this thing, gives me more time to edit it. Okay.
Apologist.
Yeah, in every sense. Okay. Now, and I introduced some notation that I think will be helpful for Thursday. So I can find A tilde 1, the superscript 1, to be the original matrix, the original augmented matrix, and I'm going to compute A2, A3, and so forth as I perform row operations. So, so for A2, A tilde 2, the entry we want to eliminate is the 2, 1 entry, row 2, column 1. So my multiplier is, and I'm going to be lazy with notation because this is going to be tedious enough as it is. You know, here I put the tilde and the superscript, but for entries, individual entries, I'm just going to use the row and column indices, we call it A21, A22, etc. So, so the entry I want to eliminate, which is a 2, 1 entry, divided by the diagonal entry in the same column. So one that's directly above it, so it's A11. So what I have here, A21 is 3, and then A11 is 1. So my multiplier is 3, so that means I'm going to subtract 3 times the first row from the second row. So row 2 is equal to row 2 minus 3 times row 1. So my new matrix A tilde 2. Alright, so now that entry in 2, 1 position is going to be 0. Although if I'm doing this in code and modifying entries of my matrix, that entry is actually not made 0. And what we'll see later is what we'll do is actually store the multiplier in there instead. But for now, we'll just be able to see the upper triangular matrix happening. And I don't trust myself to perform subtraction given my current mental state. Okay, but at least I have the results right here. Okay, so now for the next step, so I want to eliminate A3, 1. So my multiplier is 3, 1 entry divided by the 1, 1 entry. So that's going to be 4 over 1. So 4 is my multiplier. So row 3 is itself minus 4 row 1. I think by the time I get to the end of this, I might have this matrix memorized. Alright, third row is now going to be 0, minus 4, minus 1, 8, then 2, and then the last row is still unchanged for the time being. Okay. Alright, so we're making headway through the first column. There's one entry left to eliminate. So for A tilde 4, we'll eliminate A 4, 1, so multiplier, and 4, 1 is going to be 4, 1 entry divided by the 1, 1 entry, so that's going to be 2 over 1, so our row 4 is itself minus twice row 1. So now the first column that's been all zeroed out. Okay, so 4, minus 1, 7, 5. And yeah, it's a little freakish that the second column, that all those entries diagonal on down happen to be equal to -4, but that's just how the numbers fell. Okay, so now, so that means that x1 only plays a role in the first equation. It's not in equations 2 through 4. So now we need to move on to second column and eliminate those two entries below it. So for A5, we eliminate the entry in row 3, column 2. So our multiplier M32 is the 3,2 entry divided by the 2,2 entry. So our multiplier is going to be 1. And the same is going to be true for the 4,2 entry. So, in fact, I'll still write it now. Just because the numbers aren't very interesting. So this is to compute A6 to eliminate all those entries below this diagonal entry. So I'll just jump straight to A6. And you can also see what happened to the third row. So now we're not changing the second row anymore. Okay, so in the third row, we're going to get 0, 0, minus 2, 1, 1, and then 0, 0, minus 2, 0, and 4. Okay, so now the matrix is almost upper triangular. We just have this one entry to eliminate, and so we see that the two entries, we can use this one to eliminate this, they're equal, so the multiplier is again going to be 1. So M4, 3, so row 4, column 3 is going to be equal to 1. So now we just have one last row operation. Okay, so A7. So final upper triangular matrix. Okay, and then our right-hand side that's been modified as well. Okay, so now we can perform back substitution with this upper triangular matrix U. So this is U, and then the updated right-hand side is your Y. So how that's going to go is you start with X4, so it's going to be Y4 over U44. So it turns out to be -3, and then we have x3, and this is not a no, so let's write it out here. So we have y3 minus u row 4 column 3, no, row 3 column 4 times x4, all divided by u33. So we'll fill in what it is. So it's okay, 1 minus 1 times -3, all over -2. So we get minus 2. Okay. And then x2. So we go to this row, so it'll be right-hand side value, y2 minus, and then we need these two entries, so row 2, column 3, x3 minus u, row 2, column 4, x4, all over u22, so we get 1 minus 1 times x3, which is minus 2, minus 7 times x4, which is minus 3, divided by minus 4. Okay, so we get 21. Okay. Okay. 4. Okay, so we get minus 6 for that, and then finally x1. Well, diagonal entry is going to be 1, so we get y1 minus u12 x2 minus u1 3x3 minus u14 x4 all over u11, which I'll ignore in the last step because it's 1. And so we get 5 minus 2 times minus 6 minus 1 times minus 2 plus 1 times minus 3. Okay. And that's 60. Okay. Of course, the whole point is to have a computer do all this heavy lifting of creating all these things. But now you get an idea of the patterns that are used and how, now you can see, like comparing this and the algorithm that I wrote earlier, how carrying something like this out by hand can translate into code. We're using variables like I and j to keep track of where you are in the process. Okay. So any questions to this point? Kind of pre-26 review in a way. But what we'll do on Thursday is look at this from a point of view of matrix factorization, which can lead to more efficient ways of handling different situations, like I mentioned earlier, solving several systems where the same matrix, but you have different right-hand sides, things like this. Okay, so apparently I got some video editing to do, or at least video scrutinizing. So if nobody has any questions on the homework,
Just need to show you a program.
what?
I'll just need to show you the program. That's it.
Okay. Yeah, so, and apparently it's best that my brain not to try to do any more. So, okay.